Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit. Today we're going to be talking about Simpson's paradox and using that to get an introduction to gerrymandering as well. Now this week's Thursday Tidbit is actually inspired by one of the questions from the AMC 8 this year. So this is an approximate version of the question, just changing the wording, no multiple choice here, but the spirit of the question is the same. So at the end of a basketball game, Steph and Candace both shot the same percentage there. So let me just highlight our important information and we'll see how this leads to the interesting result of the problem. So at the end of the game, they shot the same percentage. But surprisingly, Steph shot better in each half. So our surprising piece of information is that Steph shot better in each of the halves there. So their baskets per half are each shown in the table below. And the problem asks us to figure out how many baskets Candace made in each half. So we're trying to figure out what's going on with Candace in this case. Now let's take a look at our information. So Steph shot 15 of 20 in the first half, 10 of 10 in the second half there. So in total, right, so if we start making out a total here, we have that Steph shot 25 out of 30. Now the problem is a little bit nice to us, and I'll come back to that in a second, but the problem is nice to us that Candace shot 12 and then 18 shots, so that means that in total Candace also shot 30 baskets. So because they shot the same percentage, so our piece of information we know right off the bat is that because they shot the same percentage, and this is why the numbers are a little bit nicer to us, Candace made 25 shots, 25 baskets as well. So that is what we know in this scenario. Now let's take a look at Steph, right? So Steph shot better in each half there. So the second half he shot 100% there, so that one is pretty easy in that case. Now, what does that mean for Candace? Well, if Steph shot better in each half, this means that Candace had to make less than 18 baskets in the second half, because otherwise she would have shot the same as Steph there. Now, likewise, these percentages and numbers aren't too bad. 15 out of 20, multiplying everything by 5, 75 out of 100. So this is 75%, or 3/4 if you like, meaning that Candace needs to make less than 3/4, or less than 9 of her baskets in the second half as well. Now, we need to get up to 25 in total, right? Remember that we still have Candace needing to make 25 in total in this scenario there. So the two numbers we have there have to add up to 25, and they need to be less than 9 and less than 18 in this scenario. So we could just start trying some numbers in this case. So let's erase our less than 18. What if we have a 17 there? Well, if we put 17 there, then 17 plus 8 is 25. Now notice that these are both the largest possible numbers, right? If we have 16 of 18, then we would need 9 of 12, which is not allowed. So we actually then pretty quickly came up, just by trying the largest possible numbers, we came up with exactly what Candace had to shoot per half there. So how many baskets did Candace make in each half? Well, she made 8 in the first half and 17 in the second half there. Now, a little note about what's happening here, right? Notice that Candace shot more shots in the second half. So even though Steph shot better, right? Steph was 10 of 10 in the second half. Candace was just below that at 17 for 18. And that's where some of these interesting things are going on. There's this imbalance there where Steph shot more shots in the second half, or sorry, Steph shot more shots in the first half, Candace more in the second half. And then some interesting things go on with these percentages there. But in total, right, they ended the game the same exact percentage. In fact, the same exact number in total as well. Now, this is a real phenomenon called Simpson's paradox. Of course, all of these things are not actual paradoxes, right? It's a paradox because it actually can happen. But you look for a certain behavior or trends are true when you divide it into groups. In each half, Steph shot better than Candace. But in total, they shot the same percentage there, right? And so that's what we have in our example here. There's a lot of other real world scenarios about this. You could have a drug that if you divide it into two types of a disease, a certain drug performs better on each type separately. But then if you look at the total numbers, again, maybe there's imbalances in numbers like we have here. Both drugs are equally effective, or maybe even the first drug is better than the other. So there's a lot of results in history where this comes up. You have some behavior that's true when you look at the groups, and this is different from the whole trend as the entire population is combined into one. So, how does this come up in terms of voting? Well, let's consider two ways of voting or looking at information, right? Well, one way would be you have a class, everyone votes. You have a school, everyone votes. You have everyone vote individually, and you collect those votes there and see what happens. Alternatively, you could divide the voters into groups, and each group gets a unified vote. So if you're doing this in a school, maybe each class decides, right? Each class has their own vote, but then at the end of that vote, the class votes as a whole, right? We're not going to get too much into actual politics, but this can make sense in a lot of scenarios, right? Our US Senate has, every state has two people representing it. So there's sometimes natural ways to divide voters into groups. And, right, Simpson's paradox says, though, that these things can have interesting behaviors, right? These are kind of similar to what we did, right? When we divided the shooting per half, Steph was better in each half. Steph won each half in terms of percentages. But in the total game, it was tied, right? Or you could have slightly different numbers, a slightly different scenario where maybe Candace has a better shooting for the whole game there. And this is what the topic of gerrymandering is all about. There's a little bit more complicated things going on, which we'll touch on in the follow-up video next week. But gerrymandering is the name that is used for the active manipulation of groups to produce a result, right? So this can happen naturally. A lot of the scenarios we're talking about in Simpson's paradox just happen based on divisions that are fairly natural and interesting things. Other forces are at play that kind of give you this interesting or quote unquote strange paradoxical result there. But right, when you come to politics and when we come to gerrymandering in particular, this is what's typically the active manipulation that changes the results there. So as your practice this week, you're going to engage in some harmless gerrymandering here. So there are a group of 15 sci-fi fans. So let's do the standard Star Trek versus Star Wars. So suppose 9 prefer Star Trek and 6 prefer Star Wars. Right? So it's accurate to say 60% prefer Star Trek over Star Wars. So 60% of the whole group prefers Star Trek, 40% prefers Star Wars in this case. Now, if we ask here, well, suppose there are 15 fans, and now we're dividing them into 5 groups of 3 people, and then each group comes up with their own answer, right? So we say, okay, then the 3 in the group vote, right? There's no ties, it's 3 people, and then they say, okay, our group prefers Star Trek, or our group prefers Star Wars. Now, questions to think about this week, and we will answer in the next video. So show that the 15 people can be divided so that exactly the 60% of the groups prefer Star Trek over Star Wars. So you can divide the groups so that the same result happens. 60% of the people preferred Star Wars. This translates to 60% of the groups prefer Star Wars. But here's where the gerrymandering comes in. See if you can come up with other results. Try to divide these people into the groups so that maybe even more than 60% prefer Star Trek. Maybe less than 60% prefer Star Trek. So see what other results are possible there. Thanks for watching. Stay tuned for the answers to those questions and a little bit more discussion next week. If you liked this video, please subscribe to our channel. That really helps out. And share any new ideas, right? Thoughts, movies, video games, sports, events happening in the real world, and challenge me to come up with a Thursday tidbit talking about those things in the coming weeks. Thanks for watching. Goodbye.